Welcome to Mongoose channel. Today I'll show you how to implement remote device control and firmware updates over MQTT. I'll be using an STM32 development board. Visit mongoose.ws and open Mongoose Wizard. Start a new project. Select the target directory where the generated project will be stored. Choose the target architecture STM32 H573, but you can use any other board. The procedure is identical. We could use Zephyr or Cube as the build environment, but let's stick with the bare metal makefile to keep things quick and simple. Choose a blank dashboard, click Next, then click Finish. On the Settings tab, disable the Web UI and HTTP as they are not needed, and enable MQTT. Note that by default, the HiveMQ public MQTT server is used. Click Generate. The wizard creates a bare metal project in your output directory. Start a serial console. Run make build flash to build and flash the binary. Debug logs show that we have successfully connected to the MQTT server. Open mongoose glue.c file, which contains the default MQTT implementation that we can override. There are instructions in the comments. Let's read them. This implementation creates a very simple MQTT client that subscribes to the RX topic, waits for messages on that topic, and echoes the received message back to the TX topic. If you want a more advanced example that implements device management, with the dashboard web page, let's open it, and with the device code, let's open it too. The device code includes instructions. Let's follow them. Number 1. Visit Mongoose Wizard, enable MQTT, generate project. We already did that. Number 2. Copy-paste this code into your main.c. Number 3. After Mongoose init call, add initialization. Number 4. Build, flash, and run the serial console to see the logs. Okay, run make build flash. Number 5. Visit MQTT dashboard. We can see that a new online device has appeared. Click on it. Try to toggle the LED. It does not work because the default code does not attach the LED handler to the hardware. Let's do that. Open main.c. Find the RPC state set function, which sets the device state. Add a line that synchronizes device state variable with the LED pin. Bump the firmware version to 1.01. Run make build to build the firmware binary but not flash it. Open browser developer tools to see what MQTT messages we are sending and receiving. Use the firmware update button on the dashboard to push the new firmware. We see that the device reboots and now the dashboard displays the new firmware version. Test the LED toggle and it works. Congratulations! We have implemented a simple MQTT-based IoT fleet manager. Now let's explain how it works. This diagram shows the setup. There are two components, a visual dashboard, which is a single web page. Here's the source code. The functionality is in the single main.js file, which is less than 500 lines of code. The second component is device firmware, which we just built and successfully updated over MQTT. The web page uses MQTT library to connect to the MQTT server and subscribes to the root topic /hash, which is a wildcard topic. That allows the dashboard page to receive all messages from all devices. Each device subscribes to the root topic /device ID /rx. It expects JSON RPC requests on this topic. The TX topic is for the RPC responses. Using Rx and TX, we implement a request-response paradigm on top of the MQTT's publish-subscribe. Lastly, the status topic is for the status updates, when a device changes its state or goes offline or online. Let's see what happens when we toggle an LED. Clear the console, toggle the LED. We can see 3 messages: a request that asks a device to set LED status to true, a response to this request, and a notification about the state change. If we update the firmware, The dashboard takes the bin file, splits it into 4 kilobyte chunks, and sends them one by one. We can see a long list of messages handled by the RPC OTA upload function. This function expects JSON frames with 3 attributes: chunk, which is a base64 encoded chunk of the firmware, offset, which is the offset of this chunk in the firmware file, and total, which is the total size of the firmware. When the first chunk is received, we call mgota begin function. On all subsequent chunks, we call an mgota write function. And finally, on the last chunk, we call the mgota end function, which finalizes the update. Since Mongoose has a built-in OTA support for a variety of microcontrollers, including STM32 series, this simply works without any extra effort. This is how you can build an IoT fleet management effortlessly. Instead of the Hive MQ server, you can use any other, such as AWS IoT or your own private server. Hit like and subscribe if you found this video useful. Thanks for watching and see you in the next video.